Hello everyone, welcome to the third video of this tutorial on decision trees. In this video we are going to see how we can use the entropy that we learned in the previous video. So recall that we are seeking the way to assign some sort of score to every variable such that we can use the best variable every time we need to choose the node. And we said that we are going to use something based on the entropy. So how we can use the entropy to select a variable? Let's assume we have this data table. If we separate the table according to one specific variable, for example, gender, we can see that we obtain this case where if we take a look to the class, we sort of have an understanding on how good was the variable gender to classify the two different classes, in this case occasional and frequent. Same thing here, if we separate the table according to the variable income, now we have three subtables, and we also can have an understanding of the quality of the income variable for classification. So notice that when we separate the table according to one variable, we have different cases. In this case, sometimes it's very good. For example, when the income is lower than 100, then we get all the cases in one class. That's very nice, because we could even have a very basic model saying, if your income is lower than 100, then the client type is occasional, because from the training set, we can see that all the rows belong to the same class. But in other cases, the same variable is not so good, as in these two cases. What we are really going to use to choose the best variable, it is called information gain of a specific variable, and is heavily based on the entropy. So don't worry if you don't understand this formula now, because you will understand it later with an example. But basically, this formula is saying the gain of a given attribute or variable A is going to depend on two big terms. The right term is basically telling us how is the entropy of the class when we instantiate the variable A on its different values, and we calculate the small entropies of the small tables. And the first term tells us what is the initial entropy of the class. Another way to see the information gain is that this calculates the difference in class entropy between one level of the tree and the level below when we separate the rows according to that variable. So again, I'm trying to give some intuitions on what is the information gain pursuing to calculate the quality of this, or the score of a variable. Now we are going to see one example, and it's going to be much easier to understand. Let's go back to our table. First, what we need is to calculate the entropy of the class. In this case, the class is the client type, and the entropy is calculated, as you recall from the previous video. We need to go over all the possible rows and see the frequency or the amount of cases in one class and in the other class, and we get the proportion. So in this case, the proportion of cases in the occasional class is 5 out of 8, and the proportion of cases in the frequent class is 3 out of 8. So we need to subtract them, and then using the entropy formula, and then we obtain 0.95, which is a bad number, right? Because recall that the entropy is close to 1 when we have maximum clutter. In this case, we have already that several cases belong to one class and also several cases to the other class. So it's a complicated class at this point. So now let's assume we are going to calculate the information gain of the variable gender. To do that, we need to instantiate the variable gender in its two possible values, and then obtain two smaller tables. And we have to look at the entropies of each of the tables. So let's calculate the entropy of the right subtable. We can see that we obtain 3 rows, 2 of them belong to one class and 1 to the other. So using the entropy formula, in this case we call the entropy of the class given that the gender is man, we have minus 2/3 log of 2/3 and minus 1/3 log of 1/3. This is 0.91. Again, it's not a good number, and you can see makes sense because out of 3 rows, 2 of them belong to one class and 1 to another. Let's now calculate the entropy of the left table. In this case, from the 5 rows, 3 of them belong to one class and 2 of them belong to the other class. So applying the entropy formula, we obtain 0.97, another bad number that indicates high clutter. So now, according to the formula of information gain, we must average, right, the entropies of the smaller tables. Actually, it's a weighted average, right, because we need to multiply each of the entropies by the amount of rows or the frequency of rows we have in each case. And now we must subtract that weighted average from the original entropy, the one we calculated a few slides ago, which is the entropy of the class without instantiating any of the variables. So recall that the weights applied into the average are obtained from the amount of rows that are present in each of the tables. That makes sense because, in other words, it's telling, if we got a given entropy from one table, but if that table is much bigger than the other one, we need to consider that somehow. So the best way to do that is to multiply the value of the entropy of this table by a weight according to the amount of rows present in this table. So in this table we have 5 rows, and in this table we have 3 rows. So this is why we get 5 out of 8 and 3 out of 8. So now, substituting, we just obtain the information gain of the variable gender by applying the formula and substituting the entropies. So here, the information gain is very low. It means that the variable gender is kind of bad for classification, as the opposite of entropy. And the higher the entropy, the worst is the variable. In the case of information gain, it is better when the number is higher. And makes sense because most of the entropies that we obtain from instantiating the variable gender are really high. So it means that after we know the values that the variable gender takes, the entropy stays high. So that means that the information gain is low, or that means that the variable is bad. So as a summary, recall how we obtained the information gain of the variable gender. We had basically to calculate 3 entropies. The initial entropy of the class here, then the entropy after we instantiate gender into man, and then the entropy after we instantiate gender into woman. And after having the 3 entropies, we basically average the entropies after the instantiation and subtract that value to the initial entropy. So this is why we say that the information gain is the expected reduction in entropy of the class, because this is an expected value, same as weighted average, right? And we are subtracting this from the original class. So we are seeing how much we reduce the entropy of the class when we know the values that the variable takes. So let's apply the same thing to calculate information gain for the variable income. In this case, we must instantiate the variable income in the possible values it takes, and we obtain 3 tables. And again, we have to look at the entropies of the class on each case. So for the left table, we have a very good case. All the rows belong to the same class. In that case, we know that the entropy is 0 because we have 3 out of 3 and 0 out of 3. By definition, this is 0, and this is also 0. Now the middle table, we have out of 3 rows, 2 belong to one class and 1 belong to the other. This is not a very good case, and as we saw before, we obtain an entropy of 0.91. And regarding the right table, this is the worst case because we have 50% of the cases in one class and 50% of the cases in the other class. And this, we know that is the maximum possible value that the entropy of a binary classification problem can take. Remember that from the plot of the previous video, that when we have 50% of proportion of one class, we get entropy equal to 1. So substituting, as we did before, we obtain an information gain equal to 0.35. So finally, to choose the best variable, we just need to choose the one with highest information gain. In this case, is the variable income because it obtains a 0.35 information gain. I encourage you to calculate the information gain of the variable place.